this well-known duality proposed by Maldacena in '97. People know this as ADS-CFT, and we discuss, okay, some issues, some points of this duality. The fact that this field theory, first of all, is in 3+1 dimensions. There are gauge fields in the adjoint of the gauge group SU and C. There are 4 fermions in the adjoint of that group, and there are 6 scalars in the adjoint of that group. The field theory has as global symmetries SO13 enhanced to SO2,4. That's the conformal group in 4 dimensions. So this is a conformal theory. It has an SO6, or you may want to call it SU4 global symmetry. People call it R symmetry. And you may want to think it as a symmetry that rotates these 6 among themselves, or rotate these 4 among themselves. It has the largest possible number that for this theory can have of supersymmetries. Again, this is a global symmetry. As a byproduct of this, the theory has a gauge coupling. Let me redefine it once again here. This is the coupling. Is called Toft coupling. Is the coupling that appears in the perturbative expansion of this theory. So notice it's a nice point that it's not G and Mills, the thing that appears, but it's due to the counting. This is something we can clarify if needed. It's due to counting of how many particles are running in loops, etc. This is the parameter that appears. Okay. And this parameter, okay, it's just the number that you fix in the theory. You can fix it very large, or very small, or equal to 1. You decide, it's just a number, but there is not a change in this parameter with respect to the energy. There is not, if you want, there is not a beta function, there is not a normalization group flow, if you want. On this side, we discussed that, okay, we are going to concentrate of the full type 2B theory. We are going to concentrate in looking for solutions that contain only these 2 fields excited. By this I will mean a Maxwell field, but with five legs. That the particular solution will have a metric of this form. Where, for those of you who are not familiar, this space is called anti-de Sitter 5, and this is a pi sphere. and we mentioned yesterday that the isometries of this space are those. So you see that there is a matching between these kind of symmetries, global symmetries here and isometries there. Also, we mentioned that when you study this solution in detail, you discover that it preserves 32 supersymmetries. Right? So you see that there is a matching in here and in there. Okay. And basically the discussion closed here yesterday. I only made one point, but let me continue it here, for one very important question that came out, was that whatever is lambda on the n equals 4 side, on the string side is this radius of the space, this one here. This is the radius of ADS5 and the radius of the phi sphere. In this particular case, they are the same. What is land is related, basically in this way, to the radius of the space, or if you want, to the adimensionalized version of the radius of the space. If we are not working with these ugly coordinates, where I wrote this, so instead of putting this alpha prime here, we would reabsorb it inside there, use a more natural radial coordinate. This would be the relation. Okay. Up to factors of pi, maybe. No, just that. And this took us into commenting on the fact that if your quantum field theory is strongly coupled, that means your lambda is really large. That means that the radius of your space is very large compared to alpha prime. And we made this kind of plot where we were saying, look, in the limit of a very strongly coupled field theory, you will be working with almost the point particles and classical approximation of the string theory. Okay? And in this sense, this duality is useful, in the sense that you can avoid yourself for doing a very quantum mechanical calculation with all the subtleties and impossibilities of doing it by doing a classical calculation in a completely different system. Okay? So the points that we discussed yesterday that are typically generic to all the dualities, namely that the degrees of freedom are very different. Right? So you see here, the degrees of freedom here are the typical field theoretical degrees of freedom. Here, gravity, this kind of forms, actually the full string theory. Right? We will discuss that in more detail today. So the strong difference between the degrees of freedom, and notice they don't even live in the same kind of dimension. Right? This is a 10-dimensional theory. But the matching of the global symmetries on both sides, and the fact that when one theory goes strongly coupled, the other is weakly coupled, making this the most suitable description in this case. Okay, so those were the, if you want, the key words of any duality. So today I would like to discuss 2-3 things in the time we'll have, that are basically the following. First of all, how to make this operative. So how to get numbers from here. That would be the first thing. Numbers, or if you want, functions. How to get functional expressions about correlation functions in this field theory, computing with this. Okay, so I will just touch about that topic. And the second thing I would like to discuss in more detail, perhaps, is how to compute a very particular observable that is called Wilson loop, here and there. Right? And about the first point, about the correlation functions, where I was redoing all the calculations today for a particular example, and I think it's kind of not very useful to spend 1 hour and a half just doing one calculation. So let me not do that in detail, but I have it in my notes, so you can take a look or make copies, etc. But about the Wilson loop, since there are different things that one can quickly learn in a quick calculation that will not take us more than 10-15 minutes, we will go in more detail for that. But okay, everything will be defined and we'll go from this. Before we go into that, let me say something that might be the same view of this in a way that is maybe more affine to some of you. Okay, some of you more familiar with gravity than with field theory. So
bottom line of the middle.
Yeah. Okay. So this is going to be a very short discussion. But for some of you, it might be a more familiar way of approaching this thing. Let's go back to electromagnetism, a point charge, and some gauge field in the space, right? An electric and magnetic field. And as you know, the coupling of this point charge to this gauge field is basically a current gauge field coupling, where the current is a charge times the delta of where it's moving, the path where it's moving. All this boils into a coupling of this form, where this curve is the curve, whatever it is, where the charge is moving, and the mu is there, right? So I guess you're all familiar with this expression. Is this the case especially for the students? Yeah, good. Very good. So what you see here is a point particle that is coupling to one form that can be associated with the to form curvature, right? So this F2 is the F mu that you have written on the floor on the floor in the third level. Suppose that instead of having a point particle, you would have some extended object like a string. So the coupling is very similar, but interestingly, it couples not only to gauge fields. Let me disregard that coupling. It will couple to a gauge field with two indexes, right? Via its charge again, and the coupling will have the following form. If Q is the charge of this one-dimensional object, that when moving describes a two-dimensional surface, the coupling will be of this form. Right? So here you have a 1D object that couples to a 2 form that naturally is associated with a curvature with 3 indexes that of course you may not recognize in that way. Right? So you can see how this generalizes, right? So in principle, a p-dimensional object that when moving describes a p+1 surface in whatever dimensions of space we are, will couple to an AP+1 potential with a coupling precisely of this form. And this AP+1 will be associated with an FP+2 form. So I'm saying this just to point something that the elder people in the audience know completely well. There is no surprises here. In that solution there, we are having an F5, right? So having an F5, this Maxwell index with Maxwell field with 5 indexes, implies that we are having a Maxwell potential with 4 indexes, which implies that basically what's happening here is that somewhat we are having objects that are 3-dimensional, okay? Right? So in other words, we are having an object that being 3-dimensional occupies, when time passes, a 4-dimensional space-time, okay? These objects are called the 3 branes. Right? And a different view, and to be historically more accurate, it's the way all this was discovered or this was induced, people start to think about this, is that there are these objects in the type 2B string theory. You can have many of them together. And just in hindsight, let me have NC of them together. These objects are called the 3 branes. They are very particular objects. They have many particular things that distinguish them. And one thing that was pointed out by Polchinski in 1995 is that these objects, whenever the following combination of the string coupling and the number of objects goes very large or very small compared to 1, have 2 different, or if you want to call them complementary descriptions. One is in terms, in this case, one is in terms of a four-dimensional field theory coupled to gravity and stringy modes. This four-dimensional field theory turns out to be, and this can be computed, there is a very rigorous calculation showing you this, turns out to be this n equals 4 super Young Mills, coupled via a parameter on the string theory called alpha prime to gravity and a whole bunch of stringy modes. When that parameter is larger than 1, this system is better described by a metric and a phi form, if you want, by a background of this type 2B supergravity. This metric has a form that is really not much different, though very different, not much different apparently than the Schwarzschild black hole, if you want. Or if you want the metric for a point particle, let me not say Schwarzschild in this case. There are 4 Minkowski directions. That's what I will denote with the 1, 3. There are 6 external dimensions to them. So you see there are 4 dimensions here. There are 6 external directions that I will parameterize by a radius and a phi sphere. The metric contains a work factor, 4 dimensions, and the extra 6 flat space. This work factor, in this particular case, and this is one of the examples that is nice to work out in details if you never did it. It's given by this. So you may recognize in this H the harmonic function in 6 dimensions. Right? So if you think we are used to the harmonic functions decaying as 1 over r squared, that's because we are in 3 dimensions. If you're in 6, that's your harmonic function. And okay, this file has, as we discussed yesterday, legs in these 5 directions and legs in the phi sphere directions. Okay, and what's so when all these things were discovered, people were working with things of this sort, even more with black holes in here, and this field theory at finite temperatures. Just let me say this, though the history is truly interesting and it's very nice to go over those papers. Let me not do it here. And people were discovering, I'm talking the year 96, 95, 96, 97, people were discovering that computing correlation functions, certain correlation functions in this field theory at finite temperature was in direct correspondence with computing absorption cross sections in black holes of this form. So that's how all these ideas came about. So there is something, of course, here you do not see the space anti de Sitter 5 crosses 5. Of course, here you do not see n equals 4 super Young Mills. There is also this. So it was one of the very important contributions of Maldacena to realize that one could focus somewhat, and I'm sorry that I'm not telling this in more detail, but it takes kind of a long time, and I'm willing to discuss it with someone if you come to the office. It's a particular limit, goes under the name of the Copley limit. Where you're doing 2 things. On the one hand, you are taking alpha prime to 0, but you're also taking this coordinate to 0 in such a way that you keep this combination fixed. And you can see how, if you do that, and this is really a nice exercise to do, but if you are planning to do it, please see me, because I can tell you in more detail what's this, what's that, and what's the precise limit you want to take. You can see very clearly how on this side the anti-de Sitter part arises, and how on this side, well, you just keep the n equals 4 superior units. But okay, let me not go over this. This was just a comment on something that people here might be a more familiar take for the people here on that. So, any questions about this?
Sorry, what is written there? I can't see very
Yeah,
well. What are you keeping fixed?
So,
R over.
so you are keeping this quantity that you call u,
Okay.
and you're keeping it fixed when both go to 0, right? It could be fixed large, fixed small, right? And you see in retrospective, this u is the u I was writing there. And you see why this u has units of energy, because length over length squared, right? So it has units of 1 over length squared. So let me leave it at this, but historically and physics-wise, this is the best way of presenting the thing. And given that this conjecture is around since so long, and people one way or another heard about this or knew these things, so allow me not to go over this. I'll just present it as a duality as we did yesterday, but that's the way that gives you really physics-wise gives you an understanding of the thing. Very good. So let me keep on some comment that some question and some comment that was asked yesterday, and basically try to briefly sketch how you get information, true information. And true information, I mean how you make a concrete calculation in here. So all this is for those of you who have seen this, two beautiful papers. One even more beautiful. Both papers in 1998, in early 1998. So the content of these papers might be expressed in the following way. Suppose that you are a quantum field theorist and you only care about quantum field theory, right? So someone hands you this particular quantum field theory, whose field content is written there, and whose Lagrangian, whose kinetic terms for the Lagrangian are very canonical, and it's just in the potential where all the richness hides. So, as a quantum field theorist, the thing that you are interested is the partition function when you couple the theory to external currents. And I mean the following. So there are all these fields. You are going to write the action of the thing. So up to this point, this is just a number, but the thing becomes truly useful when you couple different operators of this theory to different currents, external currents of this theory. So for example, if the operator is scalar operator, this would be an external current. If it's a vectorial operator, this would be your typical vectorial current, etc., etc. And this is the thing that you are interested as a quantum field theorist, because from this quantity, you basically know everything you want to know about this field theory by doing derivatives of this quantity respect to the currents at different points. Actually, it's the derivatives of the log of this quantity, and then putting the currents to 0. This gives you the thing that you are interested, that's the vacuum expectation value of endpoints correlation function. Okay, so this is the thing that the quantum field theory person can then go and tell an experimentalist, I measure this. Okay, good. Very good. Very good. So the proposal of these papers could be expressed in the following way. This is the quantity that you are interested in. So the conjecture, or if you want a more, the conjecture is that one we are discussing, the Maldacena conjecture. A more formal way of expressing this conjecture is by saying that the partition function that we just written is, and this is a conjecture, this is not a theorem, this is to be identified with the partition function of the type 2B string theory on the particular space ADS5 cross S5. Now it happens that this space has a boundary, so you will have to say what are the boundary values. This is any field in the string theory. You will have to say what are the values of those fields at the boundary. So you will have to specify the values of these fields that live in the full string theory in 10 dimensions. You will have to specify them at the boundary. And the identification is that when you specify these values to be those currents, this is the identification you want to make, right? So all the fields in the theory, and there I am writing something that may make you think that the fields are only scalar, but are not vectors. Any field should be identified with a current. That field in the boundary should be identified with a current to which you are coupling different operators of this field theory. Okay? So, as it was hinted yesterday, so this is the formal version of the conjecture, by the way. As it was hinted yesterday, this quantity is really very hard, very impossible to compute. So the best people can do is just do a saddle point approximation. Yeah. So one of the best things people can do is just saddle point approximate this quantity by evaluating the partition, as we do in saddle point in quantum field theory. Just evaluate the partition function by the exponential of the action, the classical action in a minimum, around the minimum. So the classical action is the one of type 2B supergravity. Evaluated around the minimum in such a way that you are associating with the fields in supergravity when evaluated at the boundary these currents on this side. Right? So once again, what we are losing from here to here is that we are, this is again saddle point, it's just like in any quantum field theory, you are losing the true quantum mechanics, and if you want in this approximation, you are losing the fact that the string is an extended object. This is the point particle approximation of the thing. And what you are losing is that you are forced, in order for this approximation to be, at least have the possibility of being valid, you are forced to work with a space-time that is much bigger than your string. Okay? So what basically this more operative form is telling you is that if you do a very simple classical calculation, like this one, and then of course do the functional derivatives of the log of this quantity and the log of this quantity, and this is a long song and dance to go over, but it can be done, and up to here is very much operative. But if you do this, you will be computing this object on which you are interested in the very quantum mechanical regime, in the very strongly coupled regime. So this is the version of Gapsar-Kleanov-Polyakov of the conjecture. And once again, let me emphasize, this is why the thing is useful, right? This thing you would not know how to compute at strong coupling, and this thing is basically a calculation that in 2 hours you do. Right? So that's the power of the thing.
So, Carlos, one question. So when you say the partition function of the 2D string theory, you mean the sigma model approach, in principle?
In principle, not even. In reality, yes. Right? In principle, let's put this as a conjecture. This would be valid for any value of NC, any value of G string. Nobody can compute. Okay? So we go over that limit we discussed yesterday. G string going to 0 and C going very large. Okay, we go to a sigma model. Okay? Difficult to compute. Okay, well, let's go one step less in difficulty. Let's take alpha prime to 0. Okay, so there we go. All right.
Wouldn't you expect instant corrections or this first?
Well, very good. So, in principle, you may think it in this way. Instantons usually come with like this, right? So you may think, oh, okay, look, I will do it like this, right? And this is a very suppressed thing, like C to the minus n. So you would say, oh, it will disappear completely. There are examples where you can see, I have to reconstruct these examples, where you can see how this is not always so correct, okay? I'll have to reconstruct the example. We can look then afterwards. This is like saying, in the large n limit, instantons will not contribute at all, right? But you know that there are subtle issues there. Okay, so the thing that I was planning to discuss today was something about Wilson loops. And I was trying to do this discussion kind of in parallel in 2 blackboards to emphasize different things about the calculation, etc., etc. So before we go into that, any questions or comments about this? Something that I'm saying in a very unclear way. All right, so let me erase perhaps some of this. Okay. How do I bring it back? One?
Maybe one question.
Yeah, sorry.
No, it doesn't have to.
Okay.
You have the action. Do you have it Euclideanized or?
Yeah, here I just wrote it Euclidean because I know that when you do the things Euclidean, everything is healthier, right? This should not prevent you from continuing back. Okay. I always like Euclidean because it has more connection with the lattice that to me is the reality of the thing.
Does it break supersymmetry or going to the Euclidean theorem?
No, you know good examples, the instantons, right? They are supersymmetric. They are Euclidean solutions, right, of the Euclidean action F minus square, right? Not a billion. Okay, so you know. Okay, so let me go over over a discussion of Wilson loops. We'll make a break shortly, so if you have time. Okay, so let me first say this in this way. In 1973, in a very foundational paper, especially for the lattice people, because it's a paper that I think starts with the lattice story, Wilson presented a gauge invariant observable to measure the energy between two external quarks, let me call them, right? Two external particles. So you have a quantum field theory here. You come with two particles that are external in the sense of non-dynamical. If you want very heavy, so they will have no kinetic term. You put them here and you start moving them. And there will be a force among them. Right? The force could be, okay, typically attractive, but it could have different dependencies. So what Wilson is proposing is a way to quantify, give an expression for that force. And the way is via what is called the Wilson loop. The Wilson loop then. Let me first define the Wilson loop. So this is in a theory where there is a gauge field. This gauge field can be in some representation of the gauge group. And you are putting these two external and very heavy particle, antiparticle, that are in some representation of that gauge group. And these external two things are separated a distance L. Sometimes I will probably call it L quark anti-quark. And it's very important that they are non-dynamical. In other words, they are not, suppose, I'm calling them perhaps in an abuse of notation or language, quarks and anti-quarks. It's very important that they are not, if the theory were, for example, quantum chromodynamics or any other theory with quarks, that they are not those, okay? They are other fields, non-dynamical, external, right? The quarks in QCD, they are dynamical. They have a kinetic term. These ones will not. And he proposes, it's a not a very long argument to go around, that the wave of this thing is related to the potential between the quark and the anti-quark pair. Sometimes I will say what this time is now. So the idea is that you put them here, you separate the distance L, you let some time elapse, pass. So this is kind of an Euclidean picture of the thing, and then you will get them together again and destroy it. Okay? So this is the contour on which you are doing this integral. This T here is this time here, and this BQQ sometimes and very probably will slip my mind, and I will call it energy between the quark and the quark. Okay? All right. So this is the Wilson loop, very important, observable in any quantum field theory. Very good. So for example, just to give different examples, in a theory like Young-Mills with gauge group SUN for n bigger than 2, bigger or equal than 2, what you expect is that this energy, in terms of this separation, will go something like this. By the way, notice I'm saying Young-Mills, right? So this is the theory. Okay? So notice in that theory there are no quarks, right? So you are coming with these two external particles. They are non-dynamical. They do not have a kinetic term in there. If you want, they are very heavy. So it is expected that in this theory, this energy or this potential between these two things will go something like this. So linear for very large separations. And here kind of a Coulomb law, because at very high energies, this theory is almost conformal. Okay? This theory, if you are not familiar with what I'm going to say, erase this comment. The theory develops a dynamical scale. People call it lambda Young-Mills. And in this sense, the theory confines. And in different senses, the theory has a mass gap. If you want the particles that you will observe for this theory, there is not a massless one. It's not proven, but the lattice clearly induces you to think in that direction.
You get $1 million to do.
Yeah, exactly. Exactly. It's actually, the $1 million is to prove a bit more than that. First, you have to prove that the theory exists, right? That is for a mathematician. But the lattice truly induces you to think that it exists, that the potential is like this, and that the states of the theory, there is not a massless state, and the first one appears, and then there is a tower of them. So this is what people call a mass gap. Very good. If you change the theory slightly, for example, you go to quantum thermodynamics, or if you want just Yang-Mills with a quark, and this now is a quark. Right? In other words, what I mean to say, just to be clear, this field transforms in the adjoint, this field transforms in the fundamental. This picture changes quite a bit in terms of the separation. The energy between the quark and the anti-quark pair goes somewhat like this. Okay, first this kind of Coulomb law, then kind of a linear law, but then suddenly, at some energy, it will happen something like this. So basically the phenomenology here is that, okay, at very high energies the theory is almost conformal, so you would expect a Coulomb-like law. Then you will keep on separating this quark and anti-quark pair, but at some point it will be more convenient for the system to create a pair of quarks and anti-quarks, the dynamical ones, that will basically form a meson, and these two ones will live without force, without talking to each other. Okay? So this is what you would call confinement and screening. Okay? A lattice person would call it that way. At any rate, in different theories, this has different behavior. There are really many interesting different things to be said about this Wilson loop. So, and by the way, the lattice is instrumental in computing this when the theory becomes strongly coupled, right? So in that sense, that's why this paper starts with the lattice, because Wilson knows that this cannot be, that it's pointless to compute this at weakly coupled. It's not pointless, it's not informational about this or this or this behavior. And this Wilson loop tells you a lot about the quantum field theory in itself. So what we are going to discuss in the next half hour, 35 minutes, is what ADS-CFT can tell you about something like this. Okay? This particular observable. And we are going to try to go very careful about the calculation, that again is some calculation that can be done in 15 minutes. It will illuminate different aspects of the theory. We are going to discuss this in principle in this first example of n equals 4 super Yang-Mills, right? So the calculation I'm going to do is in n equals 4 super Yang-Mills, but then you will see why I'm going to do it in parallel. So to be able to generalize it to other cases, we will start discussing tomorrow. Is this clear up to this point? Any comment or question about this? John? Okay?
Yeah,
Very good. All right. So
I'm shy.
it's perfect. And you're not British, so imagine
No.
if you were British, it would be terrible. Right? All right. So there is something that I should say very emphatically. That is the following. Okay. So in this proposal of Gapsar, Cleveland, Polygon, or if you want, we can say that at the level of when we were approximating this by the point particle approximation, and we were saying this is type 2B supergravity, okay, and we compute things with type 2B supergravity, etc., right? And we are saying, oh, look, we lose this and that, etc. It should be emphasized that the conjecture is between this field theory and the string theory. For some calculations, you may resort to supergravity. Okay, good. But you should not lose sight of the fact that the conjecture is between this and this. So something that even in this approximation will play a role is the fact that the string theory has these objects, these d-branes, or even strings, fundamental strings, that at the semi-classical level could be dealt with at this level, right? So you should consider supergravity plus d-branes, strings, all the things that live in there. And this will play a role in here. Okay, so in two papers in March of 1998, Maldacena in one paper and Ray and Yi in the other, gave a proposal that is just an extension of this formalization of Gapser, Klebanov, and Polyakov and Witten. So gave a proposal to compute this object, this Wilson loop object, right? So they basically say, okay, how do we extend that proposal to compute this Wilson loop object? What they observe, the proposal is very clean, and they present it in a very brief way. But what they observe basically is that, look, this is a non-local operator in the sense that, look, you're integrating over a curve, right? It's not an operator that is fixed at one point. So I guess that the inspiration comes from that, and the fact that, okay, the string theory contains objects that are extended. So their proposal is basically the following. Let me write it. That this Wilson loop we are talking about here is related. So if you can see what I wrote before I was writing the partition function of the type 2B string, right? Okay, here what you should add are strings. So this partition function computed in the presence of strings such that they do the following. Let me try to make a plot of this space, this ADS5 crosses 5 space. So it will have a boundary that will be your 4D space time, the one we were discussing up to here. A boundary in which some of you may like to think the field theory n equals 4 lives. I prefer not to think it in that way, but okay. So the idea is the following. This Wilson loop is computed by computing this partition function where you are considering one excitation of the string theory where you have a fundamental string that is describing for you, drawing for you in the boundary precisely the curve, this one, right? Precisely that curve. And then it's doing something in the bulk and moving freely within its bulk. Just like before, this calculation is truly a nightmare. Nobody knows how to even start doing it. So they approximate this calculation by just the classical action of this string doing this. And the classical action of string, let me just remind, I guess all of you know this, is the Nambu-Goto action of string that we are going to write in a second for a particular string that is drawing this contour on the boundary, and then it's doing whatever it needs to do within ADS space. Whatever it needs to do, it will be determined by the Nambu-Goto action, by the equations of motion of the thing. Okay, so this is their proposal at this level. So the best way of checking a proposal is try to go over this calculation in detail and see where it leads. Okay? So what we are going to do now is basically study the Nambu-Goto action of string in ADS5 times S5 space, make a parameterization of it, study what the equations of motion tell you the string should do, and try to get from here, okay, so notice now that